think this SCG Eurasian Section workshop on AI and machine learning and geophysics was organized by us in myself, Alexandra, and I think there's a fair number of people. I won't be able to list them all who are very passionate and interested in the subject. The reason for making this workshop, I think it's very topical, and we also do see how I think AI is really taking over the world in the sort of in oil and gas industry, which is a little bit late to the game, but there's a lot of developments. I'm seeing this around the world and in specific areas which we're looking on, which is the seismic data enhancement. But I'm sure there's a lot of things, both in terms of the seismic, the wells, lithology, geological correlations, and many others. So I think our human interpretation greatly benefits from AI, and I think the subjects we'll listen to today, tomorrow, and after will basically be about that. And I think I welcome everybody to participate in discussions at the end of each session and the end of the workshop in terms of how people see the future of these specific areas, and what are the trends that one might see in few years, given that the development here is great. And we are in the oil and gas industry, and specifically in geophysics, are probably at the forefront of it. There is a lot more information that's being unlocked by AI, and we think we need to be proactive, trying to understand what it means. So I think I welcome everybody who is participant in the workshop.
Morning.
Morning.
Welcoming your participants of the conference. My name is Fidan Aslanzadeh.
My name is Yuan Li from COST. Okay, welcome to session A, non-seismic machine learning for groundwater and geothermal using laboratory data. I will be chairing this session with Fidan Aslanzadeh. There will be one keynote presentation and three other talks. Our keynote speaker is Oleg Ovchenko from Nvidia. He has a PhD in geophysics from King Abdullah University of Science and Technology, and he is currently a solutions architect in Nvidia. He will present on convergence of AI and physics in job applications. The floor is yours, Oleg.
Good morning, everyone. Thank you for this opportunity. It's really a pleasure to be here and presenting what we are doing at Nvidia on this matter. So I'll give pretty high-level talk because it's not the direct area of my expertise, but I'm happy to share what my colleagues are doing with respect of blending physics and deep learning. So in terms of physics-informed neural networks and some other things. So let me first share my screen. So thank you for introduction, Yan. Yeah, my name is Oleg Ovchenko. I'm solution architect for energy and Nvidia, focusing primarily on seismic applications, but the topic of today's talk is expected to be non-seismic. So we'll talk a little bit about climate modeling, reservoir simulation, and also touch seismic, since it's very relevant. First, we briefly overview NVIDIA platform. So what are GPUs and how they accelerate deep learning. Then I show three applications for physics and for deep learning, and wrap it up with NVIDIA modules. That is our framework for building physics-informed solutions. I'm pretty sure most of you heard about NVIDIA from the side of gaming and media, where most of movies are rendered on NVIDIA hardware. But a huge chunk of where NVIDIA puts its ports these days is into HPC and deep learning, AI training and inference, which pivot mostly on matrix vector multiplications that are very well realizable on NVIDIA hardware. So for 20 years, NVIDIA develops GPUs that like perfect machines to run single instruction multiple data parallelization when the same instruction is applied in a similar manner to a range of data points. So an example is, let's say, forward modeling of wave propagation, where we have to compute stencil, like tensor operations for each time step and do it iteratively. As we already seen, CPU growth capabilities is limited, and the existing growth of hardware comes mostly from the side of the GPUs and other hardware solutions. Nvidia is a full stack company, which obviously pivots on its graphical processing units, but also a very important part is network, because when you work on a single machine that is fine for research purposes, then you don't need much of interconnect. But when you scale up and have multiple nodes or supercomputers, networking gets as important as the compute itself. These are then assembled into ready-to-sell solutions, which run low-level libraries such as CUDA on GPUs or Docker on data processing units, which are then build the base for higher-level frameworks such as Rapids for data science, which basically mimics Pandas and Scikit, but GPU accelerate, and deep learning frameworks such as PyTorch and you name it. And above that, there are already solutions dedicated for energy, for smart cities, and so on. So another interesting thing that I find my work not possible without is the GPU cloud. So some of you probably use Docker containers and Docker images to build your environments. So you might use virtual environments from pip or Docker. And NVIDIA GPU Cloud basically provides optimized, ready-to-use compiled images, PyTorch, and various other useful things like modules that we'll also mention today. It's also ready to just do Docker pull, and you get something that you can run out of the box. I highly recommend looking into it. And finally, first slide about energy. We do research and applications in basically all mostly needed areas of energy, starting from utilities and ending with upstream. And now we'll talk through each of these boxes one by one slowly. And yeah, of course, I'm joking, because we will be just touch a little bit about seismic imaging, resource simulation, and talk about climate. That is not listed here at all, because all we know that seismic data sets are huge. So these measure hundreds of gigabytes, terabytes, and vanilla applications, vanilla parallelization is by taking CPU computational kernels and translating them to GPUs using CUDA. That is like a building block, like a library that helps to accelerate, to run codes. Here is an example of one of the most successful and most needed applications, that is reverse time migration, where you have to run seismic modeling twice to place reflectors into their proper place in the subsurface. This application shows multiple speedups that are getting higher with each new optimizations, introducing new architectures. Like recently during the GTC is the NVIDIA conference that takes place every year. The company introduced new architecture, new GPU architecture called Hopper. So the previous one was Ampere, next one is Hopper, that pushes this speed up even higher. Let's say for reverse time migration, or when you're chunking any 2D domain, you typically work with HALs. So you take a patch of the data and you need to get some extra areas from around it that is called HALA. New architecture has a dedicated block that does the separation for you, so the coding gets more simple. That is nice. Yeah. Let's look at deep learning. Numerical methods, they accurately, the conventional numerical methods, they accurately describe physics, and this is the way to go when you need superior accuracy. But still, when you sacrifice resolution, you also sacrifice accuracy on using this method. When we talk about pure deep learning, like end-to-end, when you pass input data in the input and produce some output and try to find the hidden relations between these two, you sacrifice physics. This might work well when we're talking about wave propagation, for instance, for really short time steps. But and then as you move forward in time, you'll have much more discrepancies because physics would not hold. As some of you probably know, there are physics-informed neural networks, which unlike supervised methods, are trained in an unsupervised fashion. And their loss function actually encodes the equation and the law of interest. This might be Darcy law, this might be wave equation. Yeah, the benefit is these methods are meshless, so we are not tied to a specific grid sampling at the inference stage, because the input data to it are basically coordinates, time steps, and media properties where you would like to run forward modeling, for instance. So yeah, this is what we will talk a little bit about today. The first application is, as I mentioned, seismic wave propagation, work done by my colleague Harpreet Sethi. What he was doing, he was exploring how to run acoustic modeling in arbitrary medium by using pins. So on the right, there are two parts of how this solution builds. So there is a feed-forward neural network, which is given a set of input data. Then it produces the output that is then compared with the result of substitution of the same parameters into exact wave equation. And then the difference is backpropagated. And at the inference stage, if you have like a 2D domain, then you can unfold each coordinate into like a long vector along the batch dimension, pass it all at once to the network, and then you will produce the full wave field for the select time step at once. So, but you have to formulate the equation itself, its initial and boundary conditions. The wave field obviously here looks pretty good with difference that might not be sufficient for some applications. So for some applications, but for some it might work. There is a huge room for improvement, and it's work in progress. We're just trying to identify the potential, because pins and Fourier neural operators, they might be applied anywhere where we have wave equation. And so if there is a problem, there might be a solution for it. The next example of where similar approach is used, basically exactly the same, but with a different equation encoded with the loss function, is reservoir simulation, work by my colleague Clement Etina, who aims to run reservoir simulation. The idea is that there are injector wells and producer wells. Injector wells inject water, producer wells extract oil, and given initial state and flow rates at each of these wells, we want to know how the reservoir would look like in a year, 2 or 5 years. So conventionally, you would discretize your simulation domain like in cells, and then try to build a linear system which connects block cells one with another, solve this system of linear equations, and you're done. So with higher resolution, your computational efforts would be the multifold of what you would do on sparse grid. If there is a way how to do it, maybe not that accurately, but with better scaling, when you move to high resolution, this would be a really nice thing, because it might be then applied both to forward simulation and solving history matching problem. The network here is obviously not a rocket science network; it's a feed-forward network that accepts initial parameters and coordinates needed for reservoir simulation, and outputs saturations, pressures for given time step. And here is how the output looks like. This is obviously a toy problem, which shows the potential. On the left, this is modeling using pin. By the way, for both previous example and this example, my colleagues gave proper talks where all the math defined and low-level details are provided. So this talk was given at the Rice University by Clement. A previous talk by Harpreet was given at GTC last year. So the takeaway by looking at these two images is that they are not identical, these two simulations, but the distribution of pressure looks pretty similar. We have to admit that color bar here is not fixed. So that's why colors do not match that well. But at least we see that the pressure steadily keeps increasing with time, going from injection wells to production wells. So this is what we want to see. However, ultimately, this simulation by pin should match explicit solution. Then the trained forward model, like I just shown, might be used. History matching is basically inverse problem. Here is the part. So you can run a reservoir simulation instead of inverting the huge pentadiagonal matrix. You get approximate solution by pin and expect that it will be sufficient to produce the desired outcome. Another application that in the last one here is climate model. Why I added it here is because it's very much faces the same problems that we would have when going from coarse resolution being a full goal in seismology or reservoir scale in exploration. So what they do, they try to simulate atmosphere flows on global scale. And by using jointed transformers and Fourier neural operator, when increasing the resolution, the problem complexity grows. very fast. And with existing hardware approaches, it will take time a lot of time to move to extremely high resolutions. For these problems, if we want to see how this would work, if we would like to see it during our lifetime, we need to tolerate some inaccuracies produced by physics-informed methods. So the first component authors of this work that is also done by Nvidia and was presented at conference, GTC conference this year, is Fourier neural operator. What it essentially is, if you take the input data and create a simple encoder network, then instead of working in that encoding domain, you can convert to Fourier domain, remove higher frequencies produced by the Fourier transform, work with lower frequencies, pass them into nonlinearity, and then decode it back into the original domain by doing inverse Fourier transform. And by doing this, you won't be tied to specific grid resolution. So that's why, as I understand, it's called an operator, because by being trained on a coarser grid, you might apply this method at high resolutions. The second component is transformer architecture, which is probably also, grows from recurrent neural networks, but where connectivity between terms is removed. Their beneficial feature is that they can find dependencies between items that are very far offset from each other. But basically, you have to do positional encoding. So to let the architecture know, let the network know from where each piece was extracted. And in the essence of transformers is a attention mechanism, which, like in its original version, is basically a dot product between encoded patches of images. If we look at this particular example to find how these are relevant in some latent space. So if you train some supervised model for classification and look how, let's say, input images from any well-known dataset would be distributed in this space, you will see that they will be clustered. And the closer these points are in the latent space, so the higher outcome of the dot product you'll get, meaning that these vectors are better aligned and they are more similar. This is in core transformers, and authors of this work, they modify the attention mechanism based on that product by using this Fourier neural operator by multiplying something in Fourier domain. To be honest, I'm not very well aware about low-level details. Takeaway from here is that at the fine scales that are not feasible to be run on modern hardware, they get pretty decent approximation produced by the physics-informed model. And this is not just simulation, but how can we use it? So Nvidia now puts significant efforts into digital twins. So the ongoing effort is to make a digital twin of Earth, basically where atmosphere, oceans would be, their interaction would be coupled, physical laws. So we hope to see some resolution and to be able to predict like hazards, natural hazards in the real time. This solution has two key components. It's the Omniverse, which basically connects physics, geometry, visualization, and collaborative work that multiple people can work on the same project at the same time. Physics-informed neural network that give a good approximation of how the physics should look like. And since this topic is of high potential and high interest, there is a framework called Modulus, which already implements all this complex stuff, various physics-informed network, AFNOs, FNOs. It's available online. I am pretty sure all of you use like PyTorch or TensorFlow. These are frameworks. So you just load a library in Python and then predefine what you would like to do. You don't have to run to code backpropagation yourself. You work on high level. The same idea is behind Modulus, where you basically do imports as you would do conventionally with other frameworks, define model geometry on high level, define wave equation, how like the formulation would like to have, then run, and then train and run it all within the same framework. Yes, you can see here from images on the right, an interesting byproduct of in training is a network when it was not given like information about reflective boundaries, it will not model reflections. So you can get absorbent boundaries by default. So it was mentioned somewhere in papers. So that's basically it. Numerical simulations are the way to go, and obviously the standard when we need high resolution, and it's well parallelized these days in almost all industries. But physics-informed neural network, they step in where we need to do something which would tolerate like mild inaccuracies or some inaccuracies, but may be applied at impossible scale at these days. Integrated with some other concepts of building, recall digital twins. This just opens the room for simulation and visualization of something that is hardly doable with what we are using today. So that's it. Thank you very much for attention. For low-level technical details, please let me know. I'll ping relevant guys, or you can watch their talks. They're public. And once again, thank you for your attention.
Thank you very much, Oleg. Thank you very much for your nice presentation. And if you are having any question, please post it in the question and answers window. It's on the bottom line of the Zoom webinar chat. We have a question from Alfonso Reis. This has been about processing and algorithms. What about storage of the seismic data? Any offers on OSDU, Open Subsurface Data Universe?
Thank you, Alfonso, for a very nice, for a very relevant question. Work a lot with seismic data compression. Maybe you ever heard of NVComp. NVComp is the open source library that explicitly is tailored. It works well with seismic data compression as well. So there are various algorithms. A few of them are proprietary, but they're available in the compiled version. One of them is BitComp. OSDU, to be honest, I never heard of it. So what we are looking at now is which formats would be most suitable for efficient data storage for deep learning. At least I cannot talk for everybody, but this is what I was looking at, which specific format, because SegWire is, it's the standard, but when you want to do deep learning, you need parallel access from, you need to read specific pieces of data by multiple threads. I was looking into ZAR format and open VDS and open something else. But regarding OSDU, to be honest, I never heard of it personally, but I'm pretty new to the subject. So probably my colleagues, somebody can be more relevant, can give a more qualified answer to that. Thank you for your question. Yeah, but I would look at compression library and become really good.
Oh, okay. So maybe you can discuss it during the discussion question. Okay. So Alfonso Reis, that's right. VDS is very efficient for storing data. OSDU is more about standards.
The next speaker is Savinis Marasin from Intosphere Inc. And Colorado School of Mines. He will be talking about leveraging laboratory data and explainable machine learning to investigate the limitations of Gasman fluid substitution model. The floor is yours, Savini.
Thank you. Hello, everyone. I'm Savini Singha. I'm a data scientist at Indosphere, and the work that I'm presenting today is work that I did during my postdoc with the Department of Geophysics at Colorado School of Mines. This was a collaborative effort with Drs. Manika Prasad and Jyoti Behura. So the work that I'm presenting today is leveraging explainable machine learning to investigate limitations of the Gasman's fluid substitution model. And we did this as part of the Department of Energy funded SMART initiative. So as you probably already know, understanding the effects of fluid type and fluid saturation on elastic properties play a very important role in interpreting remote sensing data. And we resort to the Gasman's fluid substitution model for this a lot of the times. A good thing about the Gasman's model is that it is able to provide fairly robust approximations subject to several assumptions. A limitation is, of course, that these assumptions can get violated in real-world conditions, resulting in approximation errors. In our study, we wanted to see whether we can use laboratory experiment data to get some insights into these limitations of the Gasman's model. For this, we used 5 published data sets of fully water-saturated sandstones. And do a data-driven investigation. One way is like a traditional way where you do a deep dive into the data, you draw a lot of scatter plots and do a thorough correlation analysis, and that will probably give you some insights into some of the important patterns that are there in the data. But in our research, we were a little curious to see whether we can use some sort of a machine learning approach to sort of automate this process. The hope was that by doing this, we'll be able to extend this type of study to different types of minerals and also fluid types. This, we used an approach based on explainable machine learning. So what's explainable machine learning? Let's talk about regular machine learning first. Like when we think of methods like deep learning based on neural networks or tree-based methods like XGBoost or random forests. An issue we are facing with these approaches is that these are black box models. So you train these models and come up with predictions using the model, but at the end of the day, you don't have an understanding of how this model actually came up with this predicted value. We don't know what happened under the hood. So explainable machine learning is in some way trying to address this issue. It acts as a somewhat an explanation interface to the black box machine learning model, which gives us some insight as to why or how the machine learning model made its decision. So for an example, here I'm using a toy example of a black box cat classifier. So basically, if you give an image, this classifier is just saying, is this a cat or is this not a cat? In this case, having an explainability method can be used to get an insight to why the machine learning method for a given image actually made the decision. In this case, we see that the black box model made the decision that this is a cat. And it relied on the fact that this has fur, it has whiskers, and it has this cat ears to come up with the prediction. So as a user, when you see this, the explanation, this builds some confidence on your black box model, and it gives you some insight. If the model has actually used intuitive features to come up with this decision, it gives you some idea, is my model actually a physically meaningful model, and some insight as to whether this will actually generalize to other settings. Coming back to our research, now I'll explain to you how we used a workflow based on explainable machine learning to understand the limitations of the Gasman's model. For this, what we did was, as a first step, we calculated the Gasman approximation error for the different data samples. Coming to the workflow, okay, we're trying to predict this Gasman approximation error. So what is the error? It's basically the difference between the measurement and the estimation that we get from the Gasman model, the equation for saturated bulk modulus. We use a machine learning based regression model to predict this. In our case, we used XGBoost. And as inputs, we use porosity, the bulk modulus of the mineral, the dry rock, effective pressure, grain density, and the shear modular ratio of the dry and saturated samples as input. Here we don't use K-fluid as an input because we're working with all water saturated samples. We trained the regression model using lab data. We actually did a hyperparameter tuning with Bayesian optimization. And then, like, after training the model, we used an explainable machine learning method, get insights into the inputs and patterns that this machine learning model relied on to predict the Gasman error, approximation error. Okay, so the explainable machine learning method that we used is sharply additive explanations, or SHAP, which I'm going to explain later in the next slide. One thing to keep in mind is that these explainability methods are used on a trained model. So this workflow was inspired by some previous work in hydrology, where they use an explainable machine learning approach to get an understanding of the uncertainty in process-based model. So now let's quickly talk a little bit about Shapley additive explanations, or SHAP. The term Shapley comes from the fact that this is based on Shapley values, which were introduced by Lloyd Shapley in 1951. This is based on cooperative game theory. So basically what Shapley values do in a nutshell is that, say you have a team of players and they're playing this game. And if they actually win this game, they're going to get some prize money. These different players contribute to the game in different ways. They can have interactions between each other, and there can be synergistic effects, meaning that one player, its overall contribution on the game can depend on the contribution of someone else. So taking all of these into account, the Shapley values provide us with a mathematical framework which tells us how to fairly distribute this prize money between these different players. So SHAP basically extends these ideas to machine learning. Our game is now a black box model, and the prize money is the prediction, and the team players are going to be our input features. And with SHAP, we calculate Shapley values that basically explain how each input feature contributed to arrive at the prediction. And in our data set, explanations are going to be calculated for each data sample. So here I'm showing you an example of the explanations for just one data sample. Given the input, the XGBoost model predicts an approximation of the Gasman model in a Gasman model error. In this case, the error for this sample, it's negative 0.53. And these are the input features. And basically the bars that you see are the SHAP values associated with these different input features. The pink bars are positive SHAP values or positive contributions, and the blue are negative. So basically what SHAP does is that it tells you how these different input features contributed to arrive at this model prediction, starting from a base value. And the base value is generally the average prediction over the training data set. And these explanations are additive, which means starting from the base value, the positive SHAP values contribute to their output to get increased. And the negative SHAP values result in a decrease. These values get added up, and you finally arrive at the prediction of the machine learning model. So now let's get into some of the results. This is a summary plot of the sample-wise explanations. This is a little, this has a lot of information in it, so I'll explain it step by step. So the y-axis is, as usual, the input features. And here the x-axis actually is the SHAP value. Here, the different dots represent the different data samples. So if you take this first row, it is basically plotting the SHAP values related to K-mineral for the different data samples. The coloring scheme is different from what you saw before. Here, instead of coloring based on positive and negative, these dots are actually colored based on the value of the input feature. So here, basically, it's been colored based on the values of K-mineral, as high being red and low being blue. In this plot, these features are stacked based on their overall order of importance, or their overall contribution. This overall contribution is calculated as the mean absolute value of the SHAP values over all the data samples. So basically, we see K-mineral, pressure, and porosity, the highest important input features in this model, which tells us that these variables play an important role in the prediction of the Gasman approximation error. So in this study, we actually calculated K-mineral using a VRH averaging scheme, and we know that there are many uncertainties associated with this calculation. So seeing the K-mineral on the top was somewhat expected. We can also see there are some interesting patterns in these plots. For example, for porosity, we see that lower porosity values are associated with relatively high positive Sharp values, which basically tells us lower porosities are associated with higher Gasman error, which can be related to the fact that at lower porosities, assumptions related to pore space in the Gasman model can get violated. Another somewhat interesting observation we see is that for higher values of the shear modulus here, which is related to shear weakening, we all again see higher Gasman, higher positive Sharp values, which basically gives us an idea that shear weakening is associated with higher Gasman error, which can be associated with the fact that Gasman is assuming the shear modulus being unchanged has limitations. Another interesting observation is that here the higher pressures are also associated with higher Gasman error. I'm not a geoscientist, but like based on the input from my collaborators, they're suspecting that this may have some interacting effects with lower porosities. So this is something we'd like to investigate further. Overall, we can see that in this study, we see some patterns that are consistent with the known limitations of the Gasman model. But I would really like to emphasize things that we see with Sharp are in no way causal. Like the relationships that we see are dependent on the machine learning model and the data sets that we use for training. And also the patterns can be results of confounding variables. Nevertheless, we see that this kind of methods have some value in knowledge discovery. And our ultimate goal with this kind of work is that we'll be able to, by getting better understanding of the model limitations, we'll be able to guide future efforts to create better models for saturated rock properties. Thank you.
Thank you very much, Savini, for your presentation. It was very, very informative and interesting. Let's wait for a minute for people to type. Okay, I think we have 2 questions now. Philip, how do you compare SHAP, SHAP values with something like PCA?
Well, I guess like PCA is going to be some sort of a basis of the data, right? But and you'd probably use it as a pre-processing step on your data. But like something like SHAP is more or less an explainability method. So it's like you train the machine learning model and then you use it as like a post-processing step where you can kind of go back to see what the machine learning method really cared about when it was building the building the relationships in the model, like learning if it's like a neural network when it was learning the weights and everything, like what is going on. And I see that there's another question, like why I chose XGBoost rather than other machine learning methods. So like SHAP is actually like, it can be used on different machine learning approaches, like agnostic of the method. So, but one thing is that with the tree based methods, there's something called tree SHAP, which is pretty computationally efficient compared to like some of the other methods, and also like especially like some of the SHAP-based methods only are able to provide approximations as opposed to calculating actual SHAP values, like the actual value. So like it's a little straightforward when it comes to tree-based methods. So that's why I selected it.
Okay, thank you. We have one more question from Alfonso. Are we looking for values near SHP equal to 0? Is that the ideal point to be?
Well, if you're thinking of Gasman, the ideal point to be would be if the Gasman model and the measurements are actually agreed and there's no error. right? But with SHAP, it's trying to, like, I've created a model that tries to predict this error in the data, and trying to, so if the SHAP value associated with some feature is 0, for that for that sample, what it's basically saying is that feature did not have any contribution on the error. But it's just only explaining the XGBoost method that I created.
Okay, thank you very much for your presentation, Savini, once again.
Thank you.
Yeah, all right, so.
Okay, our next speaker is Sergio Andres Garcia Arias from Industrial University of Santander. We'll be talking about the use of neural networks for the exploration of groundwater in La Mesa Los Santos.
Thank you, everyone. Today I'm going to show you some results about my master's thesis, where it was made in the La Mesa Los Santos. I'm used some own data and also some data from Maria Ulloque. This work was made also with Professor Francisco Landia and Jose Sanabria. So today I'm going to show you some about general information about the area of interest and the methodology used to resolve the problem that is a groundwater problem, hydroelectric problem. And the result that we obtained using the neural networks, discussion about that some model generated to resolve that problem, and some conclusions. The area of interest is Los Santos. Maybe everyone knows about this area as the Seismic Bucaramanga. So in this area, it's very common groundwater. So the object of this project is to find that areas of more interest for the explorer. The water resource in general, the geology is that metamorphic basement, that is the Sigarashkis. From that is segmentary sequences, deposits. In that area, the principal formation of interest is the Los Santos formation, that is that Orvin, or also formation, Casablanca formation, that is that yellow color. And if you know, that's lineament as all, but some lineaments are more interesting than others. For example, Los Santos pole is very interesting because it's the contact, it's the limit from Los Santos formation and Casablanca formation. Los Santos formation is dendritic rocks and Casablanca formation is carbonated rocks. So and use data of rocks that was flux, and laboratory we measure properties. Some properties like density, electricity, and magnetic, the wave velocity, but the porosity is the more important if we talk about water resources. Think about porosity. We use we use cycler for all the properties. Today I'm going to show you only the porosity results when we ended using this neural network. With the beginning was a input layer. We consider the coordinates is y and z, and the formation and the distance, that block from the nearest pole. And we had two hidden layers and one output layer. We using the layer perception regressor. Each layer was initial with 5 neurons. We made a where each time it was trained and was added more neural networks. This look different networks generate using the 3 activation functions that we can use in scikit-learn. Today I'm going to show you only 6, the more significant, where we can see that different hidden layers and number of neural networks we obtained, and the score is could be that results of each neural network. But we also consider the statistical distribution. So we make a box plot that we can see, but also we compare with the swarm plot. Swarm plot is that we measure a laboratory. Swarm plot is the red dots. So we can see if for our first neural network, the logistic function, that we have some formations values near to 0, also a outlier in the yellow boxes. And if we plot and we generate that map, we can see that in general, the influence of the fault on some areas to the south in this, near to Los Santos fault, and the north of La Mesa Los Santos, like potential area of interest. In general, in laboratory, we obtain porosity from 0 to 25. So the map is that range. If we saw level 2, we see that we have a little less score than the previously never neighbor, and we see that other formations has values near to 0, begin to see negative values. Maybe for the Los Santos formation and Rosa Blanca formation, the result is good. The statistical distribution is great, similar to what we measure at the laboratory, but maybe could be better with some other results. Now, if we evaluate the hyperbolic tangent, we see that again negative values that could be great. Some outliers, these other formations, and general the map again shows influence from the fault, but it's very correct. So it's interesting to see that the whole influence of the fault in the results. And neural network 4, only 5 neurons in the 3 layer. We see again the sense of values near to 0 and no generalized very great. And the hospital is but not great. And these values here is very outlier from what measured at laboratory for a member from Los Santos. When we begin to use the ReLO function, we can see using the same structure that before in neural network 555, we can see that the result is very great. The statistical distribution is very similar to our swan plot, the red dots, but with some negative values in this formation. But in general, it's very great. And the map is better, showing again that the Los Santos formation is positive around the 10, and some areas are most near to Los Santos Pole is very interesting to be explored. But if we use more neurons on each layer, we can see that the result fits better with this statistical distribution, and only like these two formations, this little bit of layers, it's done great, but the result is very better. I think that is a good result. And again, we show that the near to Los Santos Pole, areas of great interest, the north of La Mesa Los Santos, Santos Formation, the results as greater. And with use of this neural network model, we can use, if we have a geological model defined, we can evaluate the porosity at depth. So if we see the first 25 meters, the porosity don't change a lot because the geological model not change too much. But deeper, we can see that each geological model change. We hope the porosity also changes, and the north area continues the greatest area of interest to Los Santos Formation, and the area near to Los Santos Falls to the south show again the interest groundwater exploration, if we consider that as porosity principal property of interest. As conclusion, we consider that the logistic and hyperbolic tangent are good activation functions, yes, but the ReLO function don't have a lot of negative values. So we can see in the other two functions, and the statistical distribution was better, more intuitive when we use in ReLO function, and it's more according with the geological model. So it's using this neural network, model number 6, we can find that the statistical distribution is similar that we observe at laboratory, and this is a very good step for beginning to retrain and use another model like TensorFlow to make more complex neural network structures. Also, that the areas that is highlighted by this model is very similar to the other outer world made that Los Santos Formation, that are the Titics, and Rosa Blanca Formation, that are carbonated rocks, are the greater in the geological potential, and the areas near to that Los Santos Pole is the more option to be able using another geophysical methods. And finally, we have to note that our geological model is related to estimate the properties of the Mesa Los Santos. So using the machine learning, we can evaluate different geological models. Also, we optimize and contribute to define a decision making and generate first different solutions. Thank you. This is the reference.
Thank you very much, Sergio, for your presentation. And we have a question for you. From Alfonso. Would one of the conclusions be that increasing the number of layers does not necessarily improve the quality of the model?
We made some tries using more layers, but we find that increasing the number of the layers of the first layer generate more better results than increasing the amount of layers. Maybe if we use a convolutional scheme, if we want to predict all the properties in one neural network model, could be a great idea to use more layers. But we was using scikit-learn. So at the moment, scikit-learn it can predict more than one property. Just one output could be generate a different output, but it is for the classifier neural network. But in this case, it's just was possible to use one output. So for that, we don't prefer to increase the amount of layers.
Thank you very much for your response. We have also a question in the chat. Hi, Sergio, interesting presentation. Do you have a definitive explanation for the better results of NA06? Is it only the activation function, or do you think there is a reason of the really best performance? Do you want me to repeat the question, or you can see the question?
I can see.
Okay.
The reason why we use the network number 6 is not for well, the activation function was a great result because we don't have negative values, but also was the hological coherence with the result, the statistical distribution. So if you know, for example, have metamorphic rock, we know that the porosity hological model was 0. So in general, for that reason, was the statistical distribution that we obtained at laboratory. But we see that not necessarily a great score generate a better model. So that was the consideration. The statistical distribution was coherent that was seen at laboratory.
Okay, and we have a third question from the unknown guest. Why does that and ReLU why does TAHN and ReLU have the same numbers of layers but different scores?
Yes, we always have to try to use the same amount of layers. We would like to see how each activation function and number of neurons in each layer change the results. So as was explained, maybe I don't go to be specific, but we begin with a neural network with 5 by 5 for all activation functions. We made a loop where of 5 tries is we begin making 5 primings. Each neural network was saved and the score also was saved. Next, we add more neurons to first layer and second layer, and was the loop. So let's see that the score was similar also because we don't define ascent or beginner the randomness of each neural network was a consideration. So for that reason, we think that all the neural networks not begin from the same bias and weights for each input and each neural network. So the randomness of those values could be represented in these different scores. If we compare, for example, that's layers, these two neural networks with same amount of neural networks and layers, very similar, but it's different also the score. If we compare, this score is the logistic and hyperbolic time is same, but the logistic have more neurons. If we compare with the time that we take to train this neural model is greater, but if we compare with that, but is again to return to the conclusion that we prefer to use a model that is statistical distribution is similar our laboratory results that was not necessarily as the greater score.
Thank you very much, Sergio, for your nice presentation. Yeah.
Our next speaker is Solomon Namaswal from Jomo Kenyatta University of Agriculture and Technology, Media University of Kenya. He will present on the role of predictive machine learning in the determination of geothermal reservoir temperature from resistivity in high temperature hydrothermal systems.
Yes, I'm ready. Thank you very much. I'm Solomon Namaswa from Multimedia University of Kenya. And what I'm presenting is part of my PhD research that I'm doing. So I'm working on the role of predictive machine learning in the determination of geothermal reservoir temperature from resistivity methods in high temperature hydrothermal systems. This work was based on in Kenya, a place called Olkaria Geothermal Field. So the reason for this research is the desire to have a cheaper and reliable method of subsurface determination of temperature based on surface resistivity. You know that we can measure resistivity method using geophysical resistivity methods. We can do it on the surface, but for us to obtain the temperature, we must drill the well. We know that we can measure resistivity on the surface, but temperature cannot be measured on the surface unless we drill the well. And therefore, if we can obtain a method that can be used to determine subsurface temperature from surface measurements, then it will be very helpful, because temperature is very important in the production of a well, a geothermal well. The higher the temperature, the higher the productivity of a well. So reservoir temperature distribution and rock resistivity depend on similar parameters, and this includes porosity, permeability, and mineral alterations. However, there is a very high variability of chemicals and physical conditions within the earth surface, and therefore we cannot have a theoretical or an empirical universal relationship between the distinct parameters, and that's why the machine learning comes in. So this is the area of the study. The area of the study was within the East African Rift, and this is the Olkaria volcanic complex. These red spots are the geothermal fields within the East African Rift in Kenya. And in Olkaria volcanic complex, the area is large. Therefore, it has been subdivided into 7 segments on the right side. So these are the 7 segments within the Olkaria field. And my research was based in Olkaria Dome fields, the farthest on the right. This is the area where I undertook my research. So temperature within the fields, more than 30 wells have been drilled, deep wells, for the purposes of energy exploitation. And these wells have been drilled at different times. The first well was drilled around in the year 2002, and the last well was drilled around 2018. So for the purpose of this work, 14 wells were chosen from the field. This is the selection of the well, randomly selected to cover the entire field. So after the well has been drilled, the first procedure is always to conduct well testing. So this well testing can be done by, first of all, pumping in the cold fluid into a well to kill the well, then to see how it responds with time. By shutting off the well, then it's given time to heal. So during that process, the temperature profiles are conducted periodically to see how the well is recovering. And from that temperature profiles in the well, we can determine areas with high permeabilities and areas with poor conductivities, so that we can know where we can get the fluids, where the fluid is entering the well. So the resistivity methods were obtained using MT and TM geophysical measurement processes, and they were collected between the year 2004 and 2016 by the company called KenGen, which is Kenya Electricity Generating Company, that has been given the mandate to manage this geothermal field. And these are the locations of the data points for MT within the area. And these are, so after data collections, some processes were done to clean the data using software such as SSMT 2000, MD data editor, and the outputs in a standard ADI files were suitable for use in the TD input for joint inversion with now the transient electromagnetic data. So for transient electromagnetic data, These are the data points within the region where the data was collected. And the processing for TEM was done using the OCAM 1D inversion. Then after the inversion, the data, the TEM and MD data were joined using for the purposes of correction of the static shifts. So now, after now I've prepared my temperature and received data, I used the data-driven discovery predictive model using machine learning computational approach to try to see how if I can predict temperature from the measured surface resistivity. This is due to inherent difficulties in obtaining standard law and equations to describe this phenomenon. And this is the model that I used, whereby we have the inputs, and the input now is the resistivity data that was measured on the surface, and the output is the temperature. But we don't know now the function that connects the two parameters. So the data-driven machine learning is now helping us now to generate this function to see how these parameters relate to one another. Then after that, I now bring in a new data that was not part of the training. So I input that new data into the AI model and see if I can get the results from the new resistivity data. So resistivity as a function of depth at particular points was generated from the generally inverted MT and TEM data. Then this is now the machine learning itself. I used the regression based on my data. So I employed SVR, ensemble, decision tree, and yeah, these are the methods that I used to see the best model that I can obtain. So for example, this is the well number, Olkare well number 901. This is the depth. I have resistivity as a function of depth. Then I have the temperature. I also have Olkare well 908, resistivity, temperature versus depth. I do have Olkare well 910 and 911. So the input is my resistivity and the output is temperature. So the model was built using Python. NumPy was used in the working with the arrays. I used the Jupyter Notebook for coding and Matplotlib for drawing the graphs, the pandas to analyze and clean the for exploration and manipulation, and sklearn was used for predicting temperature attributes from resistivity. So to test the performance of the model, I used the mean absolute error and the R squared to see which model was the best. So that this is the explorational data showing the temperature and resistivity. From this, we can see that most of the wells had temperature, very high temperature, going up to 350 degrees. And when you look at the resistivity, most of the well had resistivity that is below 100 ohm meters. So it looks like the wells have high resistivity, they have low resistivity, but high temperatures. So when I looked at the correlation between the two at different depths, this one is the depth at 1,000 meters above sea level. You can see we have two areas with high resistivity. And comparing with this is temperature, very high temperatures at two areas. This is the first point where the wells experience very high temperature, and this is the second area. When I look at the resistivity at the same points, at 1,000 meters above sea level, it's also experiencing almost similar characteristics. We have an area with low resistivity here, and also when you move to this point here, this area is also experiencing low resistivity. So the same was experienced at 0 meters above sea level. When you compare the two, high temperatures coinciding with low resistivity regions. So I went further. These are values at 500 meters above sea level, and downs we have 200 meters below that the sea level. So areas with high temperatures coincided with areas with low resistivity. So when I used the adaptive random forest prediction models, these are the results for those models. And when I look at the models, the mean absolute area for adaptive boosting gave me 46.99, while the R squared gave me 0.66. So this method could not give me the best, because when I look at 46 is really high, and 0.66 is R squared is really, it's too low. So So when I look at the graph here, you can see that the temperature, this is now the graph for this is the graph for resistivity. Resistivity was decreasing as a function of depth up to a particular point like 1,000. Then from there, it started to increase again. But remember that the temperature was only increasing. So this correlation between temperature and resistivity is not direct, because at a particular point, the resistivity started increasing, but the temperature continued increasing as we go down with depth. So we need a good machine learning model that can be able to predict this particular point here, whereby when we start increasing in resistivity and the temperature is increasing, this model should also be able to detect that, learn, and give me the best output. So adaptive boosting was unable to learn from that, because when I look at this is the adaptive boosting, which is this one here, it never learns that the temperature as the resistivity started increasing, temperature increased. It never learned, so it failed at this particular point. And this is well number 906A. But when you look at now the random forest was better, because at least it learned that as the resistivity changed from going down to going up, it learned and it coped up. It tried to cope up with the actual. The red one is the actual measured temperature. So this is the predicted values. So this one was better as compared to adaptive boosting. So when I go to, this is well number 908 with the same, you can see that adaptive boost was unable also to learn, because the values at this particular point, when the resistivity changed from decreasing to increasing, it continued. It almost flattened. It never changed to, it was not increasing. However, random forest gave me a R-squared of 0.758, which was a better performance as compared to adaptive boosting. So I tried also, when I tried to get a scatter plot, I was expecting a smooth line running probably from 0 onwards, because I was expecting the actual versus predicted temperatures to be the same, but it was not. So I tried a different method, which is now the SVR. Now using SVR, I was able to reduce the mean absolute error from that 6 to around that 4, and increase the R-squared to 0.789, which is a better performance as compared to ensemble methods. So you can see here that the trend is the same, the trend of resistivity increasing as a function of depth, but at around between 1,000 to 1,500 meters depth, the resistivity started increasing again. You can see now the SVR values, the predicted values, as I compare with now the actual values here, it was also popping up, and the temperature was increasing despite the change in behavior of resistivity. This is a well number 906A, and the same can be observed in well number 908. So if I compare now the scatter plots, you can see now it's behaving better as we compare it to the random forest and the other post models. So this one was almost giving me a straight line here. So this one performed better. I also now tried the DTR, the decision tree regression model, and I was able to reduce the mean absolute error from 34. Yes, please.
Solomon, you're running a little bit out of time. Could you please go to conclusion? We have only 1 minute.
Okay, this was the last. So you can see that this performed better as compared to the previous. So DTR model was able to learn the trends of the decreasing resistivity with the depth, and it started, even if the depth started, the resistivity started increasing, it was able to learn. So this is the scatter plot, which is also better. Now, I also tried now to bring in the new data that was not part of the training, and this is how it behaved. It gave me the value of R-squared of 0.8. In fact, it performed better than even the training model itself. So training the data model using a DTR algorithm approach provided a superior output. And this was based on the mean absolute error and R-squared statistical performance indices. And therefore, DTR algorithm could be implemented in high temperature hydrothermal systems. Thank you very much.
Thank you very much, Solomon, for your presentation. Dear participants, if you have any questions, please address them into the question and answer window. Okay, well, let's wait for a little bit more. Thank you very much for your nice participation and presentation. Now we have a question. Alfonso, it's not clear to me, how do you apply this technique without drilling a well? Could you explain?
First of all, what we had, there was the data for temperature and resistivity. So I wanted to know if indeed I can use resistivity to predict temperature. So if I have resistivity, can I use it to predict temperature? And from what I have used, I had to train the model first. And if the model has performed well, it means that we can use the same model now in an area where we have the surface resistivity, but we have not drilled the well. So we don't have the temperature at that particular point. But we can now use this model that we have trained to apply in that area.
Okay, so I guess this was one question. And again, so let's not hold up the conference. So let's move to the next panel session, and we have a break now. Thank you very much for your attendance.
Thank you very much.
Two co-chairs today is Ulvia Abdul Karimova and myself, Nazim Abdullayev. And we have 1, 2, 3, 4, 5 sessions and discussion at the end. So we'll start with, and sorry if I pronounce not correct, Rwanta Ratnayake from University of Oklahoma and Vietnam Petroleum Institute, machine learning characterization of a gas sand using random forest. Floor is yours.
Yeah, hi, thank you. Thank you for the introduction. So our studies on machine learning characterization of a gas sand reservoir using the random forest method. So as we know, machine learning methods are the latest coming methods in the reservoir characterization, and the artificial neural networks has been increasingly used in reservoir characterization, but there were several difficulties associated with this, such as higher running time, overfitting, and selection of many hyperparameters like number of neurons and number of hidden layers. So the random forest was identified as a method to overcome these such difficulties in the NN method. So random forest is a supervised machine learning method. It's an algorithm that can be used for both classification and regression. So in this particular study, we applied the random forest method to predict the porosity and the permeability of a Miocene gas sand reservoir in offshore Vietnam. The reservoir is the Nam Can San Basin in offshore Vietnam. So the petrophysical characteristics were predicted, that is the porosity and the permeability was predicted based on the well-log data of gamma ray, resistivity, sonic, density, and neutron porosity. So the porosity and the permeability predicted by this method was compared along with the measurements taken from core samples at different depths of the reservoir. Moving on to the study location. So the hydrocarbon in Vietnam was previously mainly produced from fractured granite basement reservoirs, which was in the Chu Long Basin. So, but recently this trend was gradually changed, and the contribution from clastic reservoirs like the Nam Can San Basin has become more important. So the characterization of this Nam Can San Basin and clastic sands in Vietnam has been important for hydrocarbon exploration in Vietnam. This figure shows the location of the Nam Can San Basin and the well H2 where this study was carried out. Moving on to the methodology. So in this study, a random forest program was developed to predict the porosity and permeability, as I mentioned before. So the training of this program was done using log parameters, gamma ray, density, neutron phi, travel time, and resistivity, and also core data. So the predicted porosity and the permeability results were compared along with the values calculated using the conventional log analysis methods and with core data to determine the accuracy of the so-called random forest method. So this diagram shows the workflow of the random forest method developed. So first it imports the machine learning libraries and the training data. Next, it splits the imported data set into training, testing, and validation, and it scales the data. So next, it builds multiple decision trees using the training data. So in this case, we have used 80% data for training and 20% data for testing. Next, it imports the target data set and predict the well-log results using the trained forest for this target data set. Next, it computes the R-squared value between the predicted and the actual well-log results. So the actual well-log results are here. Here are the core results, core data that were taken from the reservoir. So the random forest code was developed with multiple number of decision trees. So the figure here shows a diagram of a decision tree. So a decision tree is a structure that is used in the decision making process. This decision tree structure starts with a node and then it branches to another node, and it repeats this process until a leaf node is reached. So a leaf node is the end of a decision tree, or it's also a node that can no longer have any branches. So normally in random forest, the accuracy of the predicted results changes with the number of decision trees used. So we needed to find out the optimum number of decision trees to get the most accurate results. So moving on to the results and discussion, this is how we determined the optimum number of different decision trees. We calculated the R2 score for different number of decision trees. So the R2 score here is for the results predicted by the random forest and for the core data. So in here you can see that the maximum R2 score is for 6 and 8 number of decision trees. So we selected 6 as the optimal number of decision trees for the analysis. And then we trained the program and predicted the porosity and permeability. This was the results that we obtained. And the left side figure shows the porosity and the right side figure shows the permeability. So the black color curve here in the left side plot shows the porosity of the core samples that were taken, and the red color curve shows the porosity that was predicted using the random forest method developed in this study, and the green color plot is the porosity that was calculated using the conventional well-log methods. So as you can see here in porosity, both conventional well-log method and the random forest method have given accurate answers, have accurately predicted with compared to the core results. But the random forest method is more closer to the core data than the conventional log method. So in the right side figure, it shows the permeability. So in this case, there's a considerable difference between the permeability calculated using the conventional log method and the random forest method. So the accuracy is considerably high in the random forest method. So we compared this accuracy based on the R2 value. So the values for porosity and permeability calculated using both random forest and conventional log methods were compared with core values to determine the accuracy of each method. So the porosity, both methods provided outputs with good accuracy. As you can see in this table, the R squared value for porosity has been quite high for both methods, but for permeability, the R2 squared of random forest method is considerably high when compared to the conventional log methods. So these R2 squared values are obtained by comparing these values predicted by these two methods with the actual core data. So we have also calculated the running time for these random forest methods. As you can see, the running time is really low for both the cases. So moving on to the conclusion. So in this study, we have used the random forest to predict the petrophysical characterizations in the Nam Concern Basin in the offshore Vietnam. The random forest was trained using the gamma ray, resistivity, sonic, density, and neutron and core data. So this trained random forest was used to predict the porosity and permeability for the reservoir, and it was compared along with the core values to determine the accuracy based on the R squared values. So it was, we were able to observe that the porosity and permeability calculated using the random forest method was more accurate than the values calculated using the traditional log methods. And it was considerably large difference for permeability than of porosity. So therefore, this random forest method can be recommended as a more accurate method for well-log interpretation than the traditional conventional calculations method. So that's it. This is the study that we have carried out. So that's with my presentation. Thank you.
Thank you. I think there are some questions in Q&R. I don't know if you could read that. This question on what explains the disparity between core and data and log data.
Okay, so this right figure shows the difference between the core data and the log data. So the core data the permeability for core data was calculated in the lab, and the log data was calculated using the PoroPerm method. The difference between these two methods has made this difference in the results of the log and the core data for permeability.
There's another question. Don't know if you see it. It says, good topic. I've also tested the same machine learning algorithm. How do you select the input log curves? Should we select all the log curves available?
I think he's referring to the input well-log data. So in this case, we have used gamma ray resistivity, sonic density, and neutron. So in here, we have selected particular well-log data that has influence on porosity and permeability. So that's how we selected. We didn't select all of them. We selected the well-log data that has influence on porosity and permeability of the reservoir.
Okay, there's another question there. Your data stops at 4495. Why your machine learning algorithm follow the log data rather than the core data? Actually, that's the question I also wanted to ask, because you stop at 4495, but the data continues. So presume you couldn't train the data on the core after that, right?
Yeah, the core data wasn't available for the whole depth. So the core data was available from 4460 meters to 4495 meters. So that's why it's plotted at that range. And we predicted the results even beyond that depth for porosity and permeability. Due to the unavailability of core data, we couldn't plot the core data beyond 4495 meters.
Okay. Any other questions from? I don't see it. Maybe panelists can ask. Maybe I'll. Okay. So just a question again. At that below 4495, you didn't have the core data, so you didn't train on the core data, but the resistivity. Sorry, the random forests follows the log data, whereas above that point at 4495, they are actually quite different. Yeah. So here they are very different because it's more close to the core data, and there's a disparity between the core and the log, between the random forest and the log on the permeability. But at the bottom, they are quite close. Yeah.
Yeah. For porosity, it's quite the same, and
porosity the same. Yeah.
Yeah, but for permeability, we can observe in the top the log data is quite dispersed. But when it comes to the values beyond where core data is available, the two values lie on each other.
Okay. If there is no other questions, and I don't see them, thank you very much. I think that'd be great. Olivia, do you want to introduce the second speaker?
Next, we will have Kaique Carvalho from the Universidade Federal da Minas Gerais.
Can you see my screen?
Yes.
Okay, thank you. Yeah, the name is correct. It's Kaique. So good morning. My name is Kaique Carvalho. I'm from the Federal University of Minas Gerais, and I'll present this work called Resistivity Logs Influence in the book density estimation using artificial neural network. This work is sort of an extension from my master's dissertation, where I work on using machine learning techniques or artificial neural networks to estimate the bulk density log by having other curves as input. So this work I developed here with my colleagues, José Jadson and Carolina Barro. So the motivation for this work is basically on the density log, as I mentioned. So it's very important, for example, to calculate the acoustic impedance and the reflectivity. Because if you have the density log here, and if you have a velocity log, which can be calculated from the sonic log, and multiply them, you have the impedance, and with the impedance you can calculate reflectivity, and you can use check shots from VSP logs to convert it to time and do a convolution with a wavelet, and you can do a well to seismic tie, right? Calculating a synthetic seismogram. So just one of just to mention the importance of the density log. So, but it has some problems when you are measuring the density log on a well, because sometimes you have the walls caving here. It can cause some problems when you measure the density log. You have the problems with mud filtrate and things like that. So it's very important to have another option when the density log is not available on the well. That was the focus of my master dissertation. So we already have in the literature empirical equations to calculate and to estimate the density log, and the most famous is Gardner's from 1974, that we can estimate the density log from the P wave velocity information. We have a more recent work from 2019 that we estimate the density log not only from P wave velocity but from shale volume fraction as well. It's a modification from Gardner's equation, and we have many others. We have Broca's equation. So my master's dissertation focused on comparing these empirical equations to a artificial neural network approach, to a machine learning technique, to see which one can estimate better the density log with a minor error. So the objective of this particular work here was an extension. So it was to build an artificial neural network model to estimate the density log by having different well log curves as input, and to compare the density log estimation when we add to this curve the resistivity curve. And here, just to mention on the previous presentation here, one of the questions was how to choose these curves as input. So for example, for my master's dissertation, we chose based on the empirical equations. So we saw which curves were used on the empirical equations, and we use that to choose as input for the neural networks and to compare. But here at this work, we try to add more curves and to see to test how it improves the model. So just a quick overview about neural networks, about perceptron. Most of people here already know this, but the first artificial neural networks that we have knowledge of is from McCulloch and Pitts. We have the perceptron, which is basically a simulation of the biological neuron. So we have we have one vector or one array as input. We have also another array as weight. So we multiply them, we add by a bias, and we have here our activation function. And so this is sort of a fully connected network. So as many of you already know, is mostly based on matrix multiplication. All right. So if we have more than one neuron on the layer of the network, so we have not only an array of weights, but an entire matrix of weight, and that will be multiplied by our input, added together, sum with the bias. Here we have an example of very simple activation function, step function, right? But the one used in this work was not this Hebside function, was actually log sigmoid and rectify linear function. And so the training of the networks, basically we have this picture is, I think it's very good to explain. This is our supervised learning type of network. So the training data, we have the input and the correct output, right? The expected output. So the input goes in the neural network with the weights initially with random values, and this will be compared with the correct output, calculate the error, and we use an optimizer to update the weight, right? To try to minimize this error here. For our methodology for this work, we use well-logged data, well-logged curves from the campus basin in Brazil. So we use data from 5 wells for training and 1 for validation. And just to explain here, the algorithm that we used was from MATLAB. So when we choose these 5 wells, the algorithm already separates them into training, validation, and testing the data from these 5 wells. So this other well here, we separate to get a result, kind of a blind test or a second validation. The architecture of our neural network was very simple for 2 layers only. So the first layer we have 25 neurons, and the second with only 1 neuron. Then we have our output. There will be our density log. And the optimizer here was Levenberg-Marquardt method to update the weight. So we use these 2 neural networks here. So the first, and we compare the networks in this case. So the first network will take as input the curves of P-wave velocity, shear volume fraction, and the neutron porosity. And this is based on the empirical equations. There we don't have the neutron porosity, but this is one we added at the neural network to test. And we compared it with a second neural network, the model that was created. And this one, we added the resistivity log. Here's the induced log. So we compare, so at my master dissertation, we compare with the empirical equations. Here we're making the comparison with 2 neural networks to see how the addition of the resistivity log, how it affects the estimation of the density log. So here are the results. So here we have the comparison between the density, the measured in blue, and in red we have the estimation of the artificial neural network. We have here the relative error, and here we have the comparison of the density with the second artificial neural network model that takes as input the resistivity log as well. So we can see that it's a better fit here in the picture. We can also see that the mean squared error was decreased with the addition of the resistivity log as input during training. So for the first neural network model here, the mean squared error was 0.01, and for the second here was 0.006. So conclusion that we have is that the addition of the resistivity log as an input value for the regression, right, the neural network model decreased the error for the bulk density estimation. And we also conclude that this resistivity log contains some valuable petrophysical information, which is very important in generating this good fit for estimating the density log. And we expect to have in the future more studies about different curves and how they influence on the estimation of the density log. So that's all for today. I'd like to thank you very much. I will have time for questions.
Okay, thank you very much for the great presentation. Are there any questions? Okay, I guess we can maybe move to the next presentation, and at the end there will be discussion and summary, maybe if you have any questions.
Okay, thank you very much.
Fenyu B he's in lockdown. Had a friend send his presentation for us since he cannot be here.
The title of the article I want to share with you today is Fully Automatic Identification of Complex Lithological Pore Depths Using Deep Convolutional Neural Networks. My presentation will be divided into 4 parts. The first part, digital log physics. The second part, relative walk. The third part, deep convolutional neural network model. Finally, application of pore depth identification. The first part, digital log physics. So what is digital log physics? Digital log physics is a 3-dimensional data body representing multi-scale pores and the minor composition of rocks in an image and digital form. So what is the problem of existing petrophysical method? Conventional petrophysical methods have been unable to meet the needs of complex rock type evaluation. It's difficult to finally characterize the physical parameters of rocks with nanoscale pore structures such as shale oil and shale gas by conventional petrophysical experimental means. At the same time, there are still technical difficulties in complex lithological reservoir pore type identification part related work. For the identification of pore types, there are three main methods. Firstly, the method is traditional image processing, that is earth extraction. For the input SEM image, people usually use some filters to filter the input image, such as solar private, robots, and canning operators. After filtering in the spatial domain, we will get the earth information of different types of pores in the image. Then our professionals will observe the earths and make the final identification. Secondly, the method is object detection model. The method is based on a deep convolutional neural network. For the input SEM image, we will use a deep convolutional neural network as the feature extraction backbone for feature extraction of images. Then we will use the feature parameter network to fuse the feature information at different scales. Finally, we will get the result. The method is semantic segmentation model. That is, we first perform a convolution pooling operation on the image to obtain the features. Then, the feature map size is scaled up to the original image size using 2x2 deconvolution in the expansion path. And finally, the class of each pixel is predicted to achieve semantic segmentation of the input image. In summary, traditional image processing has many disadvantages, such as time-consuming, stress-consuming, and low efficiency. So can AI improve the situation? The third part, deep convolutional neural network model. First, transfer learning. Deep neural network architectures are highly capable of learning features and can learn more intrinsic patterns of sample data. Pre-train the network on large datasets such as ImageNet, MS-COCO enables deep neural network architectures to find the global optima more easily. Transfer learning is to consider that when there is a certain correlation between tasks, the knowledge obtained in the previous task can be directly applied to the new task by fine-tune and can be directly applied to the new task without any changes. The transfer learning method allows the transfer of knowledge from other tasks. We call it source task to the new task. The knowledge learned in other tasks can be transferred to the target task. We call it downstream task by the transfer learning method. This facilitates the construction of mathematical models for the target task and reduces duplication of effort and dependence on training data for the target task. The network architecture. The backbone is divided into 5 stages, and each stage is accompanied by a halving of the size of the feature map. The number of each stage is 12884. The following figure shows a typical CBL convolution and a residual block stacking structure in the backbone. A convolution layer with batch normalization layer and a liquid ReLU activation function layer. A number of CBL convolution layers are connected by residuals to form a residual structure, and the N residual structures are stacked to form a residual block. So here is the object detection pipeline. The model can be divided into 3 parts. The feature extraction of shell SEM data is performed by the backbone network to obtain the feature outputs of C3, C4, and C5 out stages, which are used to input the feature fusion parameter to feature fusion of different scale targets. The features of C3, C4, and C5 stages are fused after feature fusion to get the corresponding P3, P4, and P5 outputs. Finally, a CBL convolution block is used to adjust the channel of the feature map for the final prediction. Generally speaking, feature maps at lower layers have a higher resolution and contain more location and detail information, but they are less semantic and more noisy due to fewer convolution operations. With the depth of the network increases, the deeper features have stronger semantic information, but the resolution is low and the perception of details is poor. It's important to combine the high-resolution feature maps of the lower layers with the low-resolution high-dimensional feature maps of the deeper layers. Finally, application of pore type identification. So what does our model see from images? In order to analyze the effect of our model, we visualized a portion of the network's feature maps. As we have discussed before, feature maps at lower layers have higher resolution and contain more location and detail information. With the depth of the network increases, the deeper features have stronger semantic information, but the resolution is low and the perception of details is poor. The video of the real-time detection. Okay, that's all. Thank you.
Yeah,
Where it was learning, yeah.
you know, you're from Colorado School of Mines, and you can talk about the unsupervised segmentation of CT images.
All right, as Nazim mentioned, here we're going to present a technique for unsupervised segmentation of CT images. The previous talk already mentioned about digital rock physics. So what we need with digital rock physics is great. So instead of, let's say, performing certain experiments that can take months in the lab, especially measuring permeability, if you perform digital rock physics, you can probably get that thing done in a matter of hours. So imagine the improvement in, or the gain in efficiency. But in order to perform digital rock physics, in order to perform these experiments on digital rocks, one needs to have segmented images. Segmented images as in, if you have a digital image of a rock in the form of a CT image, you should tell the code what each pixel represents, whether it represents a pore or it represents a grain, or you can go into finer details about that. But that's essentially what you need to do. And the most common way to do that segmentation, to segment that digital image into pores and grains, is to use supervised segmentation, where the user first picks grains and pores on images and then lets the algorithm come up with a model for it. The most one of the most popular softwares to perform supervised segmentation is called Elastic, with the link shown here. Let me show you what is involved in this process in supervised segmentation. All these images that I'm going to show you in these next 2-3 slides come from this Elastic website, and this image shows the GUI of the software itself. So here is an image of, let's say, of rocks. In this case, it's cells, but let's assume it's a rock. And you see certain white and gray colored grains and the pore space. And our job is to segment this image into grains and pore space. So what the user does is it loads, he or she loads this image in the software and then generates a feature map. These feature maps can be like different algorithms like edge detection or taking derivatives in different directions and so on. Once you generate a bunch of features and adds labels manually, the user selects which pixels they think are pores and which pixels are grains. And once they add certain labels, takes the input data, the features, and the user labels, and performs a segmentation, which works great. The results are good, but the issue is there is an obvious user bias. I go and do this process, the results that I generate will be different from what someone else might, because, for example, one grain for you might not be a grain for me. So there is user bias. Also, this method obviously is not fully automated, and it is quite time consuming to pick these, to generate these labels. Moreover, one needs independent training. One needs to make sure that the pixels I picked as grain are in fact grain. So one does need independent ground truth to make sure the results are accurate. Also, generalization is almost nearly impossible. Every time you go from one rock to another, let's say I go from a sandstone to a shale or a carbonate, or even just different types of sandstones, one needs to redo the whole process all over again. And so all these are significant inefficiencies that we could potentially overcome with unsupervised segmentation, where all these disadvantages could potentially be eliminated. And in unsupervised segmentation, the idea that we are using here to realize unsupervised segmentation is to build synthetic CT images and train the network using them. Let me show you how we do it through certain examples. So what we do is a background with all black values, let's say it's all pores, and then we introduce circular grains in there of different sizes and different grayscale values. And these circular points represent grains. And the image shown here is an example of that. GT represents ground truth. This is the ground truth image. And then to make it more realistic, we add noise to it. The noise is in the form of smoothing as well as addition of salt and pepper noise. Because these images are all synthetically generated, we know exactly what each pixel is, whether each pixel is a grain or a pore. And it's done in a matter of seconds or a fraction of that. So we do this. So by doing this, one can have the input and the output. So the input to the network is that noisy image, and the network output is the ground truth segmentation, which we automatically know. Here is another example where we have introduced a pyrite into the ground truth image as well. And then similarly, the input is there, the output is there, and we generate 1,000 images, such as shown previously, out of which we use a fraction for training, some for validation. The network we use is a variation of the well-known UNet. One important change we make to training this network, I forgot to mention that this is all convolutional neural networks involved here as part of UNet. And the cost function is not just a difference between the predicted segmented image and the ground truth segmented image, but also we add new factors to it by augmenting this cost function. And the first factor is the difference in porosity. We want to make sure that the porosity predicted should match as well. And so we introduce a part in the cost function that honors that porosity difference, where we want to minimize the difference in porosity. There is a third term we introduce, which is the difference in Euler number, which is related to connectivity. We find that on testing, we find that this Euler number is not very useful. The results are very sensitive to small changes in Euler number, so we do not use this in developing the final model. With the addition of porosity, we find that addition of porosity contributes significantly to improving the results. And finally, the output is a probabilistic output. So the output varies between 0 and 1. 0 corresponds to a pore space and 1 corresponds to a grain, and any number in between would give you a probability of whether it's a grain or not. So let me quickly recap. The workflow here is we generate synthetic CT images, which just takes a matter of minutes. And then obviously we design the network and train the network on these synthetic CT images. Once we have the model, we can apply it on any rocks. So let me show you some results. The first is a few synthetic examples. On the left is CT image. Then the image to its right is the machine learning segmented volume. And then is the ground truth, and it's between the machine learning segmentation and the ground truth. And the number on the top right, the 1% in this example, represents the difference, a measure of the difference between the machine learning output and the ground truth. In this case, the difference is 1%, which is acceptable, and most of the errors are confined to the edges, to the edges of the grains, interface between the grains and the pores. Here is another example. The error in this case is higher, and this example contains a pyrite grain. We know that the surface area of the grains increases, the algorithm doesn't do as good a job. The error is higher. So if this image had very small grains, the error would increase further. And that's what's shown here. The grains are much smaller now, much larger surface area for the grains, and the errors are larger because the algorithm is not able to reconstruct the grain pore interface very accurately. So let us now move to application of this model that was developed on synthetic rocks to see real city images. So the results that I'm going to show you next are completely unsupervised because we did not use any of the real city images in training the model. We trained the model on the synthetic data and applied it to real city images. The first example is that of the Berea sandstone. On the left is a cross-section from a CT image. Note that the Berea has got some pyrite grains on the top left, represented by the white pixels. And on the right is the machine learning segmented image. And the number on the right shows a phi equal to 23.1, which is a measure of the porosity computed from the machine learning segmentation. First of all, the results are reasonable. We see a pore at almost every place we expect to see a pore, and a grain where we expect to see a grain. There are certain vertical and horizontal artifacts which come from application of this 2D algorithm to different cross-section 3D volume, which we are going to ignore for the time being. This can be removed by using generating a 3D machine learning model and applied to a 3D volume. So anyways, the results here are reasonable. The computed porosity here is 23.1%, and the measured porosity in the lab is about 18%. Next is a very noisy CT image, comes from Vedder sandstone, and on the left is that super noisy image. The quality of this CT was not good, and on the right again is the machine learning segmented output. The algorithm again does a decent job. At some places, for example, over here where there is a pore, the algorithm is not able to completely recognize that it's a pore, but overall we are satisfied with these results. And finally is an example from Bell Creek, and Bell Creek has pyrites in it, and which are shown by the two white grains. And again, the porosity on the right computed from the machine learning segmented image is about 15%, and which is very close to the real porosity, which is about varies between 13 and 14%. So here we have introduced a method for complete unsupervised segmentation of CT images, where we have trained an algorithm on synthetic rocks, which can be done pretty quickly, and then applied it to real CT images. The results are reasonable, but the biggest advantages are these processes are fully automated and unsupervised and are independent of user bias. No pre or post-processing is required. However, from the results, we see that if we need to improve the results further, some post-processing might be necessary. And right now, as it stands, the method is very generalizable. As we showed that the model was trained on synthetic rocks and then even applied to a variety of real CT images. And the results were improved significantly with a cost function where we incorporated a term related to the difference in porosity. The biggest issue with these results are that small features such as small grains pose significant problems, where these high porosity samples show larger error, especially because of the larger surface area corresponding to the grain pore space interface. With that, I would like to acknowledge the US Department of Energy for sponsoring this work, and the members of the Center for Rock and Fluid Multiphysics at Colorado School of Mines. I would also like to thank these individuals mentioned, shown here at the bottom, who provided useful input to this work or provided us with CT images. With that, I'll be happy to answer any questions.
Great talk, thank you. I think we have one question here. It says, you mentioned a 3D model. Can you please elaborate?
Oh, okay, 3D model. I should have phrased that better. My apologies. So all these, right now, the UNet uses 2D convolutional neural networks, all those 2D operations. But the input images are 3D images. And so the input images are 2D images, the synthetic images, and we use 2D convolutional neural network to train on those images. And then when we apply to a rock is usually a 3-dimensional CT image. And so we have to apply it on different slices. And that you can do that, let's say, along the X direction, Y direction, and Z direction. And that's what results in those vertical and horizontal streaks. When I talk about 3-dimensional model, I am referring to the fact that instead of 2-dimensional convolutions, one can generate 3-dimensional synthetic rocks, so 3-dimensional pores, 3-dimensional grains, and then generate or devise a network that uses 3-dimensional kernels, convolutional kernels. That way you will preserve, let's say, the spatial features and spatial relation between the grains and pores. And then you can apply a trained 3-dimensional, let's say, trained model directly to a 3-dimensional rock volume without, going through the different slices along the 3 different axes. I hope that is clear. The major difference is instead of 2-dimensional convolutions, you would do 3-dimensional convolutions. The issue we haven't been able to do it is because of restrictions or lack of computational resources. For these 3-dimensional convolutional kernels, you need really large memory in excess of, let's say, 100 gigabytes of memory, and which we don't have on our workstations yet. But if we move to clusters, that's our plan, then we can implement these 3-dimensional algorithms.
Okay, I have another question here. So when you talk about these CT images, being, not using the any other CT images, but they're all very diverse. Say, I have, a simple scenario. Okay, sandstone with pores. I have sandstone with carbonate cement and pores. I have, very different grains. I have, I have different types of mudstones, pyrite, as you say, exotic minerals, and God knows what. I mean, they could be very complicated. How is that training that it doesn't really see any? I mean, if you haven't really seen anything, how would you then recognize something like a,
True, that's a great question. Yeah, Nazim, that's a fantastic question, and that is going to be a drawback. It's like, with the audience here is very well, unless the training the training data set contains an example, if the network has not seen something, it's never really going to recognize it, and that is going to be a drawback. So it is going to be important if you know that the CT image, the rock, is going to have pyrite. It is going to be important for you to have such examples in the training. So here, for example, the Bell Creek had pyrites, right? Initially, our training examples did not have any pyrite in them. So when we applied it to the Bell Creek data, the algorithm failed. It failed quite bad, just because, hey, there was pyrite and it was mixed. But as soon as we introduced the pyrite into our training examples into the synthetic data set, it started working really well. And so, just to answer your question, if you think it's going to be a special case or there's going to be something in your rocks that's not in the training, go back and put that stuff into the training, if possible.
I see Paul has his hand up.
Yeah, can we actually have him on? I don't know if
I can allow him to talk.
Thank you. My name is Paul de Groot. I'm from DGB Earth Sciences. And
hi, Paul.
Hi, nice presentation, Jyoti. I only object against the naming in the title of unsupervised segmentation. I know this is semantics, but I think this is really a supervised approach that you have presented. You have trained on simulated data, which is fine. This is one of the ways to do it. And if you can simulate, and in this particular case you can, that is fine. But the algorithm you are using is still a supervised learning algorithm. A UNet needs labels to be trained. A real
I see your
unsupervised,
point.
unsupervised method is like a Cohen network or an unsupervised vector quantizer that is clustering the data. That means you are doing the interpretation afterwards. You're just saying, here's my data, organize it for me. And once it is organized, you get a picture with all kind of colors, which still needs to be interpreted. So in my view, supervised means you're doing the interpretation up front. You are creating the labels, either synthetically or through interpretation. Unsupervised is you're letting the algorithm run and you make sense out of it at a later stage.
I see what you're saying. So in this case, although code does it generates all the labels without any human involvement, in that case, that would be semi-supervised. Is that what you're saying?
No, it's supervised because you are creating the labels. The only thing that you are doing different is that you are creating the labels through simulation. So because you have simulated the data, you know what the input and the output are, but you're giving that to an algorithm that is a supervised approach. That algorithm learns how to combine these two.
That is good to know. I stand corrected in that case.
Well, yeah, I didn't want to. I just think semantics are important because there's so much terminology in this space, and if we are using the terms in a different way, then we're getting more confusion.
Of course. I totally agree with you. It is important.
Thank you.
And point taken. Thank you.
Yeah, I think great discussion. We are sort of moving into a discussion space, more or less. So I think this is actually great. That we started this discussion on supervised, unsupervised. So maybe I'll open. I'm not an expert here. Maybe Paul is, and others are more of experts. But I mean, you've heard the talks, and we're all seeing mostly supervised learning in all of them.
I found Paul's comment very interesting. So maybe Paul or maybe other experts, examples of unsupervised learning, whether in geosciences or elsewhere.
I'm giving a talk which I actually had to give yesterday, but I think it will now be tomorrow at the end of the last presentation. It will be, and in that talk I will show supervised and unsupervised examples. Whereby the supervised examples that we have in seismic interpretation have been with us since the 1990s. And most of these techniques are applied around mapped horizons, where we just segment waveforms, pieces, trace segments extracted around the mapped horizon, and then we cluster these waveforms and see what comes out. And that that gives us a new perspective on how we look at the data. We see all kinds of colors, but these colors still need to be interpreted. And that's very similar to what you are doing, except that you can also do this supervised, but then you have to say based on attribute analysis or based on whatever you see in the seismic data, that what I'm seeing here has a certain meaning, like this is a channel, and what I see here is a levee. And if you create labels in that way, you can also create an output, but then the output has meaning because you have interpreted the data up front and you have used a supervised approach to recognize that these points that you have picked are different from the points that are clustered or classified in a different way. And again, the unsupervised method is really the easier way of generating a nice image, but it's the more complex method to actually make sense out of it, because when you get the result, it's just different colors. You still have to interpret.
Yeah. So I wonder, it's going to be really hard to apply the unsupervised learning in these things, which are the things like, let's say, CT image, identification, the pattern recognition there, or in the logs, because you're actually, or faces, because you're after actually some structure, and that would actually wouldn't create a structure you would recognize, right?
Well, if I look at these CT images, then the dark patches are the porosities, and they really stand out. So if I would do an unsupervised segmentation with a Cohen map or an unsupervised vector quantizer on such an image, I'm pretty sure that one of the clusters will correspond to the dark images, to the dark patches. And that would mean that you can apply these techniques, but then you also have to retrospectively say, okay, the dark patch that I'm seeing here is the one that picks up porosity.
Yeah, and how would you know that this method, say, is better than the say the supervised or various other methods? It has to be obviously personal. I have to look at it and decide which of the methods is better.
Yeah, that is the main difference between supervised and unsupervised. If you have labels either interpreted or modeled, then you know what you're looking at. And if you're doing an unsupervised approach, that is in most cases easier to create an output, but you still have to do the interpretation. And then the question is, how good it is. So in both instances, there is a form of bias involved, because either you do the interpretation upfront, or you do a modeling in which you are creating models that also are biased in a way, because you are creating the models. And the interpretation of an unsupervised approach is also your interpretation. That's also a form of bias. So you need to calibrate that against real measurements, like what we've seen in this presentation, that they also had a porosity prediction, and then they compared that against the real measurements. And if that happens to be in line with a lot of measurements, then you get confidence that this is a good method to apply within the bounds of the errors that are given from the real measurements. And that's the same with seismic interpretation. If you have results, if you have drilled wells, then you can use these wells as calibration points. So you know, at this location, I should have this answer.
Yeah, I think it's all about so for example, I'll probably refer to there are some talks tomorrow related on seismic data conditioning, and that obviously relies heavily on QC. Say if you have 100 wells, or that you can check the AI improved data with, then maybe people will believe you. If you don't have any data, then people won't. Well, I don't know how can would you accept it? Because I mean, a lot of it is basically a ground truthing.
Yes.
Say when the seismic improvement, the ground truthing is the wells. In the wells, I guess it's the core data and so on.
Yeah, of course. Everything that we do in our line of business is a form of interpretation. But at some point, these techniques help you to get to a better interpretation. But there's always uncertainty surrounding it, and you have to accept that. But you also have to realize that that is the case.
So, Paul, you mentioned uncertainty. Sorry, Nazim, to interrupt.
Sure.
So, have you or has anyone else looked into uncertainty quantification?
I think in a lot of machine learning applications nowadays, you're trying to get some measurements of uncertainty. In the unsupervised methods that I will show tomorrow, we get basically two outputs. One is the cluster center, in which cluster is this particular location falling, and the second one is how close is it to the cluster center, and that is a kind of confidence level between 0 and 1. We call it a match in this approach, and that gives me a confidence measure on how good is my clustering at this location.
I see. How about neural networks or in deep learning?
Yeah, in deep learning you can also do that. Basically, if you're doing a supervised approach, and suppose I'm doing a supervised approach into 4 different classes, and I would do this with a standard multi-layer perceptron. So my multi-layer perceptron has 4 output nodes, and the idea then is that I'm putting something in, and it has to fire a 1 0 0 0 if it falls in cluster number 1. And it has to fire 0 1 0 0 if it falls in cluster 2, and so on. Then I know exactly what the output should be. It's a factor of 1 0 0 0 1 0 0 and so on. And I can compare what the network actually fires with what it should be for the winning class. And that also gives me a form of a confidence. How good is the prediction? And so there are many different ways of how you can tackle that, also with deep learning algorithms.
Okay. Hey, now I can't miss your talk tomorrow or day after tomorrow.
It will be recorded, I presume.
What's interesting, for example, Jyoti's thing, because a lot of these are completely biased and completely manual. I do a lot of this interpretation of not I do, but we look at the CT scans, and it depends on the lab and a person that does it in a lab, and it's very kind of So I think getting these methods is definitely an improvement. I think we still need people to look at it, but at least it gets remove some of the bias. Sure, it's the same with petrophysical evaluation. So yeah, I think we can, if we don't have any questions, I just don't want to occupy all the space here, so we can then continue tomorrow.